Hi, I already discussed depth first search in previous lecture. Just go through that lecture, then come to this lecture. In today's lecture, I'll discuss breadth first search. Given a graph G equals to B, E, B for vertices and E for edges, and a distinguished source vertex S. Source vertex means from which vertex will start the breadth first search. Breadth search systematically explored the edges of G to discover every vertex that is reachable from S. It will discover all the vertices which are adjacent from source. It also compute distance. Distance means smaller number of edges from S to each reachable vertex. So it will find the shortest path from source to every reachable vertex. It also produces a breadth first tree like depth first search. Depth first search also produces a depth first tree or depth first forest. Here also breadth first search produces a breadth first tree with root S. It will start from the root S that contain all reachable vertices. If one tree, that is breadth first tree, if more than one breadth first tree, it will be a breadth first forest. For any vertex reachable from S, the simple path in the breadth first tree from S to V correspond to shortest path. So whatever the simple path from source to any vertex, that is the shortest path. And this algorithm work for both directed and undirected graph. Directed graph means a graph having directed edges. Undirected graph means a graph having undirected edges. And it is convenient to use a queue to trace the operation of breadth first search. In DFS, we used a stack for data structure. In breadth first search, we'll use a queue as a data structure. In queue, we can do two operations. One is NQ and another is DQ. DQ means delete, NQ means insert. We can insert at the end and we can delete from the beginning. Suppose this is a queue, we can insert or NQ at the end and we can delete from the beginning. The queue is initialized with the traversal starting vertex and marked as visited. On each iteration, the algorithm identifies all unvisited vertices that are adjacent to the front vertex and mark them as visited and add them to the queue after the front vertex is removed from the queue. So what we will do, first we will enqueue all the adjacent, then we will delete that vertex. Like DFS, BFS forest of the graph can also have two kinds of edges, tree edges and cross edges. In DFS forest, there are four kinds of edges, tree edges, back edges, cross edges and forward edges. In directed graph, we can see all type of edges, whereas in undirected graph, we can see the tree edges and back edges. But in BFS forest, there are just two type of edges, tree edges and cross edges. Tree edges is same as DFS tree edges. These are the one used to reach previously unvisited vertex, and cross edges connect vertices to those vertices before they connect vertices either on the same or adjacent level of the BFS tree. With example, you can understand tree edges and cross edges meaning are same as DFS forest. And BFS uses just one timestamp, that is discovery time or finishing time. Let's discuss algorithm of BFS. Input will be a graph having set of vertices and edges, and output will be a graph with its vertices marked with consecutive integers in the order they are visited by the BFS traversal. So output will be a sequence of vertices in which way will traverse the graph. First, mark each vertex in B with 0 as mark of being unvisited. 0 means unvisited. Then we'll take one variable count and we'll initialize at 0. Then for each vertex B in B, this is every vertex of V, do if V is marked with 0 means if V is unvisited, then BFS V. DFS algorithm and BFS algorithm have two parts, one for the function and one for the algorithm. Here this is the algorithm. Next I will discuss the function, BFS function. Function BFS V visit all the unvisited vertices connected to vertex V by a path and number them in the order they are visited via global variable count. So count is the global variable. Every time count variable will increase and accordingly will name. Accordingly will assign some number to each vertex. So count will be count plus 1, mark B with count and initialize a queue with V. Then while the queue is not empty, means while there are some vertices in the queue, do for each vertex W in V adjacent to the front vertex 2. If W is marked with 0, count will be increment, so count will be count plus 1, mark W with count and RW to the queue and remove the front vertex from the queue. So this is the algorithm for BFS. In next lecture, I will discuss example that you can understand the BFS algorithm. Let's discuss what will be running time, what will be time complexity for this algorithm. It is same as DFS. For adjacent matrix representation, it will be theta of number of vertices square, and for adjacent list representation, it will be theta of number of vertices plus number of edges. Both running time is same, just we are doing different way. In breadth first search, we are going deeper, while in breadth first search, we are going wide. In next lecture, I will discuss some example of BFS by help of Q, and I will also discuss BFS tree. If this lecture is helpful for you, please like and subscribe. Thank you.